Oh man, thought I'd have that thing down before. There we go. Those of you who see the very beginning of this video, I meant to start with a blank. Oh goodness. So anyways, that was well, you'll see it soon enough. It's my first slide for this morning. Good morning. No, good morning. How hard can it be to type good morning? It took me 3 attempts. Let me, whoa, I'm still in my lasso tool. Let me say good morning and welcome. Good morning and welcome to this, Earth Day edition of Chem lecture. We had a very interesting placement of lectures this week, Monday and Wednesday. Monday we got to have the 420 edition of class, and today 422 is Earth Day. And I always remember Earth Day because my brother was born on Earth Day. And when he was in high school, I think I gave him the best gift I will ever give him. I gave him a t-shirt that says Earth Day every day. And exactly, he loved it. And I think like he made that his goal, that he wants to live every day like it's April 22nd. Unfortunately, everyone around him doesn't. But we're going to be hanging out later to celebrate Earth Day, and him, of course, as being part of the Earth. Nothing to do with the fact that he was born today. We're going to do some nerdy things like play Magic the Gathering and play Magic the Gathering. It's the nerdy thing that my wife and I all do together. So of course, it's his birthday, it's Earth Day. We're all, for those of you who are familiar, in the Earth Day edition, we're all required to have green in our color domain because of the day and the holiday. So yeah, I don't know if this is going to become a thing, from now on, but it definitely, it's happened 2 days, in a row. I have a new daily mixtape up for you. And this was not planned. I don't want to give you the impression that I'm some kind of contrarian, that purposefully, oh, what up, Sulai? There we go. I don't want to give you the impression that I'm some sort of contrarian, that I purposefully select music that is like opposite of what you would expect on any given day. Our daily mixtape on 420 had no jam band stuff. It was actually kind of a like laid back, overcast type of playlist, not the bright, sunny Bob Marley fest that you would expect. And then our Earth Day today. I made this little mixtape before I really realized it was Earth Day. But if I were to make an Earth Day playlist, I would do like a lot of like acoustic kind of, Simon and Garfunkel rootsy type of stuff. That's what an Earth Day playlist should be. I love to hear that. Ready to learn. That is what I'm here to facilitate. Anyways, our mixtape of the day is a 3-song expose on Detroit garage rock. Not in an expose. I picked 3 bands with Jack White in it, because I was just feeling the vibe. So anyways, it's a weird Earth Day playlist. Check it out. It might make a good study tool. Or it might not, depending upon your tastes, but it's there for you or not for you. You can find the link in the description. One last piece of business, or one last piece of business. This might be our first piece of business, to be honest. I am, all caught up on lecture PDFs. So all lecture slides are in Canvas. They're in Canvas under Files. So if you are, I know only about half of you use the slides, and if you're not one of the ones who does, and you're wondering what are these slides, they're literally the finished slides from my YouTube lectures. So, I had started doing this, then I wasn't sure if it was useful. Turns out about half of you use them. So I'm going to continue to do this. After concluding each lecture, I take the slides, the layers from Photoshop, save them as a PDF, and upload them to Canvas. So if you want those as a study tool, they're available for you, and I'm currently live. Every lecture has been uploaded. I haven't done all the office hours yet, but I'll be getting there soon. I'll also be uploading this probably between today and tomorrow. So I still have some office hour stuff to catch up, but all lectures are live. You can check those out if you want to, or you can leave them be if that's what you want. All right. Let's get down to business. To defeat the Huns. We left off on Monday with a conundrum. I drew 3 different Lewis structures for nitrate. All right. And you can see them here. 3 different Lewis structures. And for the first one, you can see that I'm going to call this structure A. Middle one will be structure B. The third one will be structure C. You can see the difference between these 3 structures is the placement of the double bond. And I said, if I were just asking you to draw a Lewis structure, these are all correct answers. But I asked a more philosophical question at the conclusion of last class. And that question is, which oxygen actually has a double bond? Is it to the left, as it is in Lewis structure A? Is it down, as it is in Lewis structure B? Or is it to the right, just like it is in Lewis structure C? I posed that question, and then I gave you a confusing answer. The answer I gave you is all of the oxygens are double bonded, and none of the oxygens are double bonded. All right. And now I'm here to kind of unpack that. That was the hook, the cliffhanger, the will our hero survive type of a moment. And now you get some hopefully satisfying, resolution to that moment. So the fact that we can draw the Lewis structure for nitrate, in different ways actually tells us something about the structure of the molecule. All right. These 3 different Lewis structures for nitrate, have a very specific relationship. And that relationship is, they are called resonance structures. All right. These are all called resonance structures. All right. Now, resonance structures, the way you show that relationship is with a special type of arrow. All right. The type of arrow, it's called a resonance arrow. And it's a double-sided arrow. So it's an arrow with a arrowhead on either side. I just want to be clear. This is not down here. This is not a resonance arrow. That is something called an equilibrium arrow. All right, that's a different thing. But the way you show that these are all resonance structures, that these are different Lewis structures for the same molecule, is you draw a double-headed arrow between all of them. All right, this is an indication that we're dealing with resonance structures. And every resonance structure is important because every resonance structure gives you an insight into the true structure of the molecule. All right. Here's how. We say, oh wait, I want that in green. A molecule's true structure is what we call a superposition of all resonance structures. All right. The molecule's true structure is a superposition of all of its resonance structures. Now, this word superposition, you may or may not be familiar with. It basically means that the true structure is you take all the resonance structures, overlay them onto each other, and average them. The superposition is I'm going to put this in quotes. It's similar. It's like a weighted average. All right. It's like a weighted average. So the true structure of nitrate is a combination, is the superposition, is the average of all three of these structures. Okay. And that's why I said last lecture that all of them, all of the oxygens are double bonded in a sense, and none of them are, because in the true structure, the bond between nitrogen and oxygen is this weird averaged hybrid in between a double and a single bond. All right. They all have some double bond character. They all have some single bond character because there is one structure for each oxygen where it is double bonded. So it's almost like a third of the time it's double bonded. But in the other two structures, 2/3 of the time it's single bonded. So each nitrogen-oxygen bond has about a 1/3 double bond character and a 2/3 single bond character. All right. Now this is very abstract. This can be hard to wrap your mind around, but I'm going to give you an illustration. And because we are digital right now, it's going to literally be an illustration. I apologize ahead of time for my poor art skills. Here's the way to think about resonance structures. Think about resonance structures think about them as photographs. Different photographs of the molecule. All right. So for example, if I were to show you a picture, this is where If I were to show you a photograph of my, let's see, this would be my right profile. And then if I were to show, so here's one picture. And that's me. Here, let's give me some hair. All right. And if I were to show you a picture, whoa, of my left profile. Oh goodness. I'm trying to live up to my first profile and I'm falling painfully short. I've got better hair on my left side apparently. All right, so there's my right profile. Here's my left profile. Now you can see my skills of an artist. That was a strong bad reference, if anybody if anybody knows what that is. Thank you, Sulai. I needed that encouragement. So if I were to show you a picture of my left profile and my right profile, all right, so you're looking at them, two pictures, and then I were to ask you this question. Oops. Which one is a picture of me? If I asked you which one was a photograph of me, you would say, stupid question. They're both you, right? They're both me. But if I were to come back at you and say, hey, well, how can you say that they're both me? They look different. Look at that. One of them has its nose on the right side. The other one has a nose on the left side. How can you say these are the same thing? You would come back and tell me that these are two different pictures. These are pictures from different perspectives of the same subject. And that the answer is that I am the superposition of my right and left profile. All right. You would say, I am, me, Josh the human being, am a combination, am a superposition of both my right and my left profile. And that these pictures aren't pictures of different things. They're pictures of the same thing from different perspectives. And that is exactly what resonance structures tell us. Resonance structures are photographs of the same molecule from different perspectives, and the true structure is the combination of all of those photographs. We use all of those photographs to get a true sense of what the actual structure is. Hopefully that makes sense. Now, so that is the heart of resonance. If any of you have organic chemistry in your future, you'll be drawing a lot of resonance structures. This is a very, very powerful explanatory tool. Oh, you can hear my 18-month-old who's almost at his nap time just escaped and has started pounding on the door because he knows I'm in here, but I'm hiding because I'm working. Okay, so anyways, if you have OCHEM in your future, you will do a lot with resonance structures. It becomes a very powerful tool for analyzing a structure for its stability, for its reactive sites, etc. Raj, that's awesome. Okay, so that is resonance. Now, when you are asked to draw a Lewis structure, the way these problems will be written is I will ask you to draw the best resonance structure. All right, I'm going to ask you to draw the best resonance structure. So there often are multiple possible resonance structures. Not all of them are equal in their, not all of them are equal. Some of them are better than others. And when I say better, I mean the depictions are more stable. All right. And the true structure of a molecule will resemble its best resonance structure. Now, with the example that we did previously with nitrate, those three resonance structures, all equally valid. They all have the same amount of formal charge. They all have the octet rule satisfied. So the true structure of the molecule is an even mix of all three of them. All right. But we're going to draw many Lewis structures this semester where one resonance structure, there are many possible resonance structures, but one resonance structure is better than the rest. And I'm going to show you how to identify that. All right. How to get at the best resonance structure. First, when we talk about the best resonance structure, we need to talk about first, each element has a full octet. Each element has a full octet. All right, that is job number one of the best resonance structure. You can draw a million resonance structures where the octet rule is violated, and those resonance structures do not do a good job of portraying the true structure of the molecule. Oh, here, let's see. We got a question in here. How would you draw KNO3 or potassium nitrate? It's the best resonance structure. Are there multiple of them too? Great question, Vraj. There are multiple ways to draw the nitrate. There are multiple resonance structures for the nitrate. Potassium just floats around as a cation. Okay, so drawing the best resonance structures. First, each element has a full octet. Second, your best resonance structure, in the best resonance structure, let me try that one more time. The best resonance structure will have minimal formal charge. All right, we'll keep formal charges to a minimum in the best resonance structure. And again, every example that we've done up to this moment in time, the formal charge has been what it's been. We haven't been able to minimize it, increase it at all. But in the examples that we're about to dive into, we're going to see examples where there are multiple ways to draw the Lewis structure, and how you draw it will actually affect or we'll change the amount of formal charge present in the structure. So, so these are the two. These are the two examples that, the two things to look for when you're looking to optimize a resonance structure. Okay, I apologize for my the cadence of my talking getting all halted and off. Okay, it looks like our stream's still going. I started having some technical difficulties. How about that? Technical difficulties with the feed. So I lost. Okay. For a second, I lost my my live feed. So I wasn't sure if you guys were asking questions. So I was trying to talk and fix that. So, anyways, I've got this powered up. I'm actually still trying to troubleshoot it on the side. Okay, but let's do an example where we actually have to minimize formal charges. All right, so let's draw the best resonance structure for the following molecule. Let's go ahead and do sulfate. All right, so SO4 with a -2. Now, first step, we need to calculate our electron budget. Sulfur has 6 electrons. All right. Oxygen also has 6, but remember, we have 4 of them in this molecule, and 6 times 4 is 24. And then finally, we have our charge of -2. That tells us that there are 2 extra electrons in this molecule that wouldn't be there normally. All right. And so that gives us a total electron budget of 32 electrons. Okay. Sorry, I just realized I jumped the gun a little bit just in the as I was solving the thing on the side. Okay, so that's step number 1, right? Step number 2 is we need to pick a central atom. And up to this moment in time, we have been selecting central atoms based on the Lewis dot structures, right? So if you look at the Lewis dot structure for sulfur, 6 valence electrons, 1, 2, 3, 4, 5, 6. Oxygen, also 6 valence electrons, 1, 2, 3, 4, 5, 6. So this may look like a tie. You can see that both sulfur and oxygen have 2 unpaired electrons. That means under normal circumstances, they like to form 2 bonds. And so you may be looking at this and going, which one do I pick for my central atom? And the answer to that question is you always pick sulfur over oxygen because sulfur can make far more bonds. If you're wondering why, the answer comes through something called expanded octet. Another, i.e., so expanded octet. In other words, breaking the octet rule. I might as well be saying Breaking Bad. breaking the octet rule. Turns out there are circumstances in which you are allowed to break the octet rule. And this may come as a shock to some of you because I have been so rabidly pro octet rule. All right. I've been so like, don't ever break the octet rule. If you break the octet rule, you get a 0 on the problem. You must satisfy the octet rule. Always, 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 always. Right? And now here I am saying, well, sometimes you can break the octet rule. I feel like this is what our parents do to us, right? Our parents, hopefully, not trying to make a comment on your upbringing, but hopefully your parents raised you to think that murder was wrong or bad. Like, kids, don't ever murder. I know that bully on the playground makes your life miserable, but just please don't kill him. Don't take a crowbar to school. You shouldn't murder a bully, right? Our parents provided a very, very clear moral imperative that murder is wrong. But then you get older and you realize that 10 out of 10 of our parents, if they had the opportunity to murder someone bad, say Adolf Hitler, you've got the chance to murder Adolf Hitler and save 6 million people from being murdered. You realize that like 10 out of 10 of our parents would probably just do it. And what happened to murder is always wrong. Again, it's a sticky thing. And I told you that breaking the octet rule is always wrong. And the answer is it is, unless by breaking the octet rule, you can kill Hitler. And let me show you what I mean. So turns out you are allowed to break the octet rule for any element that is on the third period or lower. So let's look at this. Third period. 1, 2, 3. Everything that's on the third period and down can break the octet rule. And now you might be feeling a little cheated. You may be going, Josh, that means that out of 118 elements, that 108 of them can break the octet rule. All right. And I'm here telling you yes, but I also want you to understand why. All right. The octet rule, here's where the octet rule comes from. So when we talk about the octet rule, we know that on every period, except for that first one, right, there's going to be 1 s orbital and 3, that makes it look like a 3p orbital, and 3 p orbitals, and that these together let me just scoot this over. Thank you, lasso tool. That these can hold 8 electrons. All right. And that's where that octet comes from, that idea of the octet rule. In the main group, you're always going to have 1s, 3p. 1s and 3p orbitals, 4 orbitals present, 2 electrons per orbital. We can hold a total of 8 electrons, right? And that's where the idea of the octet rule comes from. Now, on the third period and lower, you run into a phenomenon known as an expanded octet, where you're allowed to have more than 8 electrons. All right. An expanded octet is exactly what it sounds like. It's more than 8 electrons. Around an atom. All right. And I want you to understand why. Okay. I want you to understand why. Take, for example, sulfur, which we'll be getting back to our Lewis structure of sulfate in a moment. Sulfur has the following electron configuration. We have a neon core for sulfur. Sulfur is, let's see, where are we? 3s2, 3p4. All right. So sulfur, looking at its Lewis structure, it's got 6 valence electrons. It wants to acquire 2 more to complete its octet, right? Now, but let's not forget that we are on the 3rd period. And on the 3rd period, when n equals 3, L can be 0, which is S subshell, 1, which is the P subshell, and 2, which is the D subshell. We don't normally write the D orbitals in sulfur's electron configuration, but I'm going to do it here. There are 5 3D orbitals with no electrons in them. And because there are no electrons here, sulfur has room in its D subshell for more than 8 electrons. All right. It's the presence of that D subshell. We've got these empty orbitals that can hold more than 8 electrons. That's why sulfur is allowed to expand beyond the octet. All right. More than 8. Raj, great question. Raj's question was, are more than 8 valence electrons or just normal electrons? And here we're talking about valence electrons. More than 8 valence electrons. Obviously, every element beyond oxygen has more than 8 total electrons. Here, we're just talking about our valence electrons. And sulfur has room in the D subshell for more than 8 valence electrons. Thank you for clearing that up. All right. Now, the reason why this starts on the 3rd period is because the 3rd period is the first period on the periodic table with D orbitals. So the 2nd period, 1st period, they don't have access to D orbitals. And so they're stuck at 8. They must adhere to 8. Now, again, you may be looking at the periodic table right now thinking the octet rule seems pretty dumb because almost all of the elements on the periodic table can break it. And I want to, even though that's true, there are 2 reasons. Excuse me, I've got the hiccups. 2 reasons why the octet rule is still of critical importance. First, just because an element can break the octet rule doesn't mean it will. Most of the main group still follows the octet rule. Most main group elements still follow the octet rule in most of the structures that they form. So just because they can break the octet rule doesn't mean they do. All right. Just because you can murder someone doesn't mean you will. And second, the second reason why the octet rule is still of critical importance is, yes, only 10 elements strictly adhere to it, but look at those elements. Carbon, nitrogen, oxygen. All right. When you, and hydrogen, right? Hydrogen, technically it's not an octet, but it still wants to, it will only ever get as many electrons as, helium, its nearest noble gas. When you think about the mass of elements in biological systems, they are almost exclusively made up of these four elements. All right. Almost all of you follows the octet rule strictly, right? Because we are mostly carbon and hydrogen with a little bit pinch of nitrogen and oxygen thrown in. This is the case for most biological systems. So even though the elements that strictly adhere to the octet rule are in a minority on the periodic table, they are the majority of elements we run into in biological systems, and they're the majority of elements that compose biological systems. So that's why the octet rule is so important, because it governs all of biochemistry, almost all of biochemistry. I can't say it 100%, but almost all of biochemistry, almost all of organic chemistry is ruled by this principle. So what my point here is, you need to know when you're allowed to break it, but just because now that you know you're allowed to, like when you realize your parents are totally fine with you taking out Hitler, doesn't mean that they're down for you to just go out and start, looking for bad people to kill. All right. It doesn't mean you do it all the time. You got to wait to stop the genocidal maniacs. All right. Save it for then. And now you know when you're allowed to expand beyond the octet rule. With that in mind, let's go back to our previous example. All right. This is why we pick sulfur over oxygen every time, because sulfur is on the third period and it can take an expanded octet. And because it can take an expanded octet, it can make more bonds. We're going to select sulfur as our central atom. Oh. All right, so now let's get back to the business of building this Lewis structure. We've totaled our electrons. We've picked our central atom. Now let's attach all of our oxygens. All right, we have 4 oxygens to attach to our central atom. 4 bonds will cost us 8 electrons out of our budget. Let's see, 32 minus 8 is 24. All right. Now you'll notice that sulfur, as drawn, has 8 electrons. It has its octet rule satisfied. But our oxygens don't, right? We need to move to the next step in drawing Lewis structures, and that is completing our octet. Now, each oxygen has access to 2 electrons, as is, right? So we need 6 more apiece. 1 oxygen will have a full octet if we can give it 6 electrons. We have 4 oxygens. 6 times 4 is 24. So it turns out we have enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have exactly 24 electrons, which is what we need to fill all of our octets. Things are going great, right? We had enough electrons. We didn't even have to do the, we have 2 less. Let's make a double bond. We're good. All right. Next step, we need to calculate our formal charges. If you calculate our formal charge for oxygen, so let's calculate it for this oxygen. For the formal charge calculation, you take the number of valence electrons an element has when it's neutral, and oxygen has 6, and then you count how many electrons it has access to in the structure. But for this calculation, remember, you give the element 1 electron per bond, and then all of the lone pair electrons. And oxygen, so we do 6 minus, oxygen has 1 bond, and then it has 6 electrons in lone pairs. So this will be 6 minus 7, giving oxygen a formal charge of -1. And if you do the calculation for each other oxygen in this structure, they will all come out to have a formal charge of -1. All right. Now let's calculate the formal charge for sulfur. When sulfur is neutral, it has 6 electrons. Now, as drawn in this structure, sulfur has no lone pair electrons and 4 bonds. It gets 1 electron per bond. So 6 minus 4 is +2. So as drawn in this structure, sulfur has a formal charge of +2. Now, before this moment in time, all right, up to this moment in class, I gave you 6 steps for drawing drawing Lewis structures. And last lecture, at first, we just did the first 4 steps, right? Total your electrons, pick a central atom, attach the others, fill the octets. Last lecture, we learned how to calculate formal charge. That's step 5. Step 6 is we need to draw the best resonance structure by minimizing formal charge. All right. Step 6 in this process is draw the best resonance structure. And that is what we need to learn how to do now. All right. I said earlier that the best resonance structure will have minimal formal charge. Obey the Octet rule and minimal formal charge. We need to learn how to do that. All right. And so we're going to learn how as we pop to this next slide. So let's look at the Lewis structure that we have drawn. I'm just going to redraw it here. With all of our formal charges that we calculated. So 3 negative 1s and 1 positive 2. Okay, Raj, you got a question. Are there cases where we can subtract 16 electrons from the bank? Totally. I'm sure there are. I can't think of any off the top of my head, but I'm confident that such a thing exists. I think so, though I no specific examples come to mind at the moment. All right, now, here is a dead giveaway that we can minimize formal charge. Whenever you run into a negative formal charge and a positive formal charge on atoms that are next to each other, this is a pretty clear indication that formal charges can be minimized. Formal charges can be minimized or reduced if, and this is an important if you have a third period or lower element. All right, if the element is capable of having an expanded octet, then you can minimize formal charge. All right, and here's how. This particular resonance structure isn't very good, because it has a negative and a positive formal charge on atoms that are next to each other. Now, negatives and positives attract. They don't want to be separated. They want to be together. All right. And so to get to a better resonance structure, here's what you do. Take a lone pair that's on the element with a negative charge, turn it into a multiple bond between the negative element and the positive element. Now look what happens to the resonance structure. All right, so we took those two electrons and turned them into a double bond between oxygen and sulfur. Everything else in this molecule remains the same. So let's draw in all of our lone pairs, which can be onerous, but you have to if you want to have correct Lewis structures. Now let's calculate formal charge. Now 3 of our oxygens, nothing has changed, so we can just draw the negatives in as is. All right. But now let's calculate formal charge for the 2 elements that experienced a change. So for this oxygen, when it's neutral, it has 6, right? And then we subtract the electrons it has in the structure. Now it has 2 bonds. We get 1 electron per bond plus 4 electrons in lone pairs. All right. So 6 minus 6 is 0. That oxygen now has a formal charge of 0. Let's calculate the formal charge for sulfur. All right. This sulfur has 6 valence electrons when it's neutral. In this structure, it has no lone pairs but 5 bonds. 6 minus 5 is a positive 1. So in this structure, sulfur has a charge of positive 1. All right. Now, when you compare these two, the resonance structure on top, the first one we drew, has 4 negative charges and 2 positive charges. All right. The resonance structure down below has 3 negative charges and 1 positive charge. We have reduced the formal charge in this structure, and we know that the best resonance structure will always have minimal formal charge, and we've reduced it. All right. We've reduced it once. Maybe we can do it again. Let's take, because you'll notice we have a negative charge on this oxygen, a positive charge on this sulfur. So let's use this new tactic that we have. Let's take 2 of our lone pair electrons and turn them into a multiple bond between oxygen and sulfur. So this oxygen now has a multiple bond with sulfur, just like the oxygen we have up top. Our other 2 oxygens haven't changed, so they still will have charges of negative 1. Now, when you calculate the formal charge for this oxygen, we have 6 electrons when we're neutral. In this structure, we have 2 bonds, 4 lone pairs. 6 minus 6 is 0. And now, when you calculate the formal charge for sulfur, sulfur has 6 electrons when it's neutral. In this structure, it has 6 bonds, so it also has a formal charge of 0. We've reduced our formal charges again. All right, we've gone from the previous resonance structure, which had 1 positive and 3 negative formal charges, to a new resonance structure, which only has 2 formal charges. Now, at this point, you may be thinking, well, we've got a great thing going. Why stop there? Why don't we take another lone pair off of oxygen and turn it into a multiple bond with sulfur, which we can do. Nothing can stop you from doing this. Let's take a look at what happens. So now we have 3 oxygens double bonded to our central sulfur. Or here, let me be more thorough. Okay. Now, when you calculate your formal charges, all 3 of the oxygens that are that are double bonded have no formal charge. But when you calculate sulfur's formal charge, sulfur has 6 electrons when it's neutral, but in this structure it has 7 bonds. So now sulfur has a formal charge of -1. We can take our lone pair off of our last oxygen, do the same thing to get one last resonance structure, which will look like this. Let's see, I'm gonna have a little bit of trouble squeezing this in, but I think we can do it. So now we have a, let's see, 1, 2, 3, 4, 5, fifth and final resonance structure, where all of our oxygens are double bonded to sulfur, and all of the oxygens are neutral. Sulfur has 6 electrons when it's neutral. Here it has 8 bonds, so now it has a formal charge of -2. And this is our final Lewis structure, resonance structure. Now, here's the question. All right, I told you that first off, the best resonance structure would have octet rule satisfied. We can expand if we need to, but you have to at least satisfy them. We did that. Then I said that the best resonance structure would have minimal formal charge. And here's our problem. For the first 2 resonance structures, we were able to minimize our formal charge. But for the last 3, the total formal charge in the last 3 structures are the same. The last 3 structures all have 2 negative formal charges. The first one has 2 -1s on oxygen. The second one has a -1 on oxygen, -1 on sulfur. And the last one has both negatives on sulfur. So they all have the same amount of formal charge. The question is, which is best? How do you determine which one is our best resonance structure? I'm going to redraw them here really quick. On the next slide. So how do we determine when we have 3 resonance structures with the same amount of formal charge, which is the best resonance structure? Right, then we have the 1 on oxygen, 1 on sulfur. Finally, we have both formal negative charges on sulfur. All right, so the third thing that you look to after you have completed your octets, minimized your formal charge, and now we have 3 structures who all have the same, they're different structures, but they have the same amount of formal charge, the tiebreaker here is the best resonance structure places negative charges on the most electronegative elements. Because the most electronegative elements want them more. Electronegative is such a long word. So when you look at the three Lewis structures, the three resonance structures we have up here, you have to ask yourself, what's more electronegative, oxygen or sulfur? And oxygen is more electronegative. Therefore, the structure that places the negative charges on the most electronegative elements is our best resonance structure. All right. Okay. Question from Vraj. One atom having all final charges. Okay. Oh, sorry. That was the leg of my desk. You go for the most electronegative element. Symmetry doesn't matter. Having all the charges on one element is neither good nor bad. The winning factor, the deciding factor is the most electronegative elements because they want the charges most. They pull on the charges hardest. They're going to get the negative charges in the best resonance structure. So I'm going to add this actually to our list of how you find the best resonance structure. First, you got to have a full octet. Second, you minimize your formal charge. And third, if there are multiple resonance structures with minimal formal charge, then you have to have the most electronegative elements bear the negative charges. All right. And this is the three-step process for analyzing, assessing your resonance structure to see if it is sufficient, if it's the best resonance structure, or if you can come up with a better one. Cool? All right. Let's take a look at let's do another example. Now that we have this knowledge, let's do another example. Let's draw the best resonance structure for phosphate. All right. Step number 1, we need to calculate our electron total. Phosphorus has 5 electrons. Oxygen has 6. But we have 4 of them in this structure. So 4 times 6 is 24. And then, don't forget, we have our charge of -3. That means we have 3 extra electrons in this structure. So we have, let's see, 5 plus 24 is 29, plus 3 is a budget of 32 electrons. Now, when it comes to our central atom, we have oxygen versus phosphorus, and phosphorus is third period. third period elements can have expanded octets. So we know right out of the gate that phosphorus is going to be our central atom. All right, we've got 4 oxygens that we need to attach. And that will cost us 2, 4, 6, 8. Eight electrons, leaving us with 24. All right. And again, oxygen needs to have 6 electrons. 6 times 4 is 24. So we have just enough electrons to satisfy everyone's octet. Right? We've spent all the electrons in our budget. Now we need to assign our formal charges. All right. Here, oxygen has 6 electrons when it's neutral, minus the electrons in this structure. It has 1 bond, so we get 1 there, and 6 valence electrons. So oxygen's formal charge will be -1. When you calculate the formal charge for the 3 other oxygens, they'll come out the same because each oxygen in this structure has 1 bond and 3 valence electrons. Or sorry, 3 lone pairs, which is 6 valence electrons. Let's calculate the formal charge for phosphate. When phosphorus is neutral, it has 5 electrons. It has 4 bonds in this structure. So that leaves us with a formal charge of +1. And we have that situation that we ran into in our previous example. You have a positive and a negative on adjacent atoms, so they're next to each other. And one of the atoms is third period. It can have an expanded octet. So we can't keep these charges apart. They want to combine. We need to take one of our lone pairs and turn it into a multiple bond, a double bond between oxygen and phosphorus. So now we have 3 oxygens that haven't changed at all. And since nothing has changed, we know that they will have the same formal charges. We need to recalculate, though, for our double bonded oxygen and our phosphorus. So when oxygen is neutral, it has 6 electrons. In this structure, it has 2 bonds plus 4 electrons in lone pairs, leaving us with a formal charge of 0. And when we calculate formal charge for phosphorus has 5 electrons when it's neutral. In this structure, it has access to 5 bonds. That's 1 electron per. So it has a formal charge of 0. And here's the thing. We've already seen in the last example what would happen if we try to make more multiple bonds to phosphorus. There's no positive charges left in this Lewis structure, which means that we can't reduce any, right? We can't combine them with a negative, make them go away. And if we make more multiple bonds to phosphorus, it's just going to shift the negative charges from oxygen, which is more electronegative, to phosphorus, which is less so. So this is our Lewis structure. This is the best resonance structure for phosphorus. Sorry, not phosphorus. Phosphate. All right, and that would be the final answer. All right, let's take a look at another example. All right, let's draw the best resonance structure for, how about chlorite, ClO with a ClO2 with a charge of -1. Let's calculate our total electron budget. Chlorine has 7 electrons. Oxygen has 6, but we're bringing 2 of them. So that adds 12 electrons to our total. And then finally, we have our charge of -1. So we have 1 extra electron in the mix that we need to spend to make this structure. So this is 20 electrons. And all right, now we can move on to selecting our central atom. Now, in the case of oxygen versus chlorine for a central atom, chlorine is 3rd period. So it can have an expanded octet, which means it can make more bonds than oxygen. So we're going to pick chlorine as our central atom. Raj, great question. So Raj just asked for those of you who aren't keeping an eye on the live chat. He said, these are easy. Are there any difficult ones that are exam caliber? And believe it or not, every example I've done today has been exam caliber. I just misspelled caliber, and now I can't edit the comment. So that is that is embarrassing. All of these have been exam caliber. There are a couple tricky ones that I'm going to do after. That I'm going to do, like, but it's subtle. Like, these problems don't get wicked hard. And as you'll see, there's like some subtle things to watch out for, but it's not terribly bad. So all of these have been exam caliber, can totally show up in the exam. And then I'll do a couple and you'll see it's like, oh, there's a twist there, but it's not insanely hard. You won't have to go super saiyan to beat this problem. So we have our central atom. We need to connect our atoms to our central. This is going to cost us 4 electrons. So 20 minus 4 leaves us with 16. Now, our oxygens need 6 electrons each. We've got 2 oxygens, so we have enough. We have 12 to complete their octets. So 16 minus 12 is 4. And now we turn to chlorine. And then chlorine has 4 electrons. It needs 4 more. And check it out. We actually have 4 in the budget. So we can just give chlorine, our central atom, 2 lone pairs. And we're good to go. All right. We've satisfied everyone's octet. Let's calculate our formal charges. Oxygen, when it's neutral, has 6 electrons. In the structure, it has 1 bond and 6 lone pairs. So oxygen will have a formal charge of -1. Chlorine, in this, when it's neutral, chlorine has 7 valence electrons. In this structure, it has 2 bonds, so we get 1 per bond, plus it has 4 electrons in lone pairs, so 7 minus 6 is a +1. And again, we have a 3rd period element with a positive charge right next to a negative charge. We can draw a better resonance structure. We can minimize our formal charges by making a multiple bond between oxygen and chlorine. So again, drawing out our Lewis structure. One of our oxygens hasn't changed, so we know it'll still have a formal charge of -1. Calculating for chlorine, we know that chlorine has 7 valence electrons when it's neutral. In this structure, it has 3 bonds and 4 lone pairs, so it has a formal charge of 0. And then oxygen 6 valence electrons when it's neutral, minus 2 in the bond, plus 4 in the lone pairs, comes out to be 0 as well. So this is the best resonance structure for chlorite, the molecule. Okay, a couple questions. Okay, first, Sulfate, does exam 3 usually have a higher average than the first two? It totally does. Part of the reason, I think, this is at least my working theory, maybe just my hypothesis. But with exam 1, I'm pretty sure exam 1 is actually the easiest test. But it doesn't have the highest average because people are kind of like surprised, like, whoa, it's exam 1 and stuff is hard. And they're not used to the test taking style, so the average is usually low. Exam 2 usually has the lowest average period, because I think it's material-wise is the hardest test. One thing you'll notice about exam 3, the material that we've been covering so far, is the only math we've been doing is counting. And we'll get back to some stoichiometry that'll show up at the end of the semester, probably. But it's a lot of conceptual stuff. So the math and the stoichiometry that made exam 2 so brutal, is going to be only a minor component of the third exam. So it does tend to have the highest average. Sulfate, that is a great question. If you look at chlorine in this structure, it has 3 bonds and 2 lone pairs. So that means in the 3 bonds, we have 6 electrons. In the 2 lone pairs, we have 4. And when you add those together, that's a total of 10 electrons in this structure. So here, chlorine has an expanded octet. So it's breaking the octet rule by having more than 8 electrons. Not lower than the third period. It's including the third period and lower. Everything beneath the second period. Lower than the second period can have an expanded octet. So I've been saying third period and lower. So that means that it includes the third period. Hopefully that makes sense. Okay, Raj, you said, where was that? Can I do acetate next? I totally can. Now, acetate is a little bit of a different compound, because acetate is an organic molecule. Organic. Oh my. Okay. Acetate is an organic molecule. And so the method that I've been teaching, the method presented in the Tro textbook of selecting a central atom and all that jazz, is a way of looking at and kind of constructing Lewis structures for inorganic compounds. Acetate is organic. So often you'll see it written like this, CH3CO2, the negative charge. And this is telling you something. It tells you something about how the molecule acetate is connected. It doesn't have a central atom. Acetate doesn't. Most organic molecules don't. Almost all of them don't. So when you look at acetate, you build it a little bit differently. You still total your electrons, right? We've got 2 carbons, 4 electrons a pop. Oh, wait, but we've got 2 of them, so that's 8. so 8 electrons. We have 2 oxygens, 6 electrons apiece, so that's 12. And then we have 3 H's, 1 apiece, so that's 3. And then we have our negative charge, which brings 1 additional electron, giving us a total of 24 electrons in our budget. Now there's no central atom, but we do have 2 carbons. And to connect those together costs 2. In the molecule acetate, you can see the way this is drawn. It tells you that the 3 H's are all on the same carbon. And then the 2 oxygens, are also on the same carbon. So we go 2, 4, 6, 8, 10. Leaving us with 12. Now both both of the oxygens have 2 electrons. They need 8, so they require 6 more. So to fill the oxygen octets for our oxygens, we need 12 electrons, and that is the remainder of our budget. So we can go minus 12, and now we're out. No more electrons. The problem is that our second carbon atom here only has access to 6 electrons, so its octet is not full. Whenever we're missing 2, we know what to do, right? You take your lone pairs, turn them into a multiple bond, and that's how we get the following structure. All right. Now when we calculate formal charges, everything in this molecule comes out to 0 except for that carbon with 3 lone pairs. So there's 1 formal charge. You could go through and calculate the formal charge for each atom, but I'm going to skip that step in the interest of time. Okay, let me see a couple questions. Sulai, for organic, wouldn't you draw with the line structures or whatever it's called? Totally. So yes, so organic structures are best, described by their line structures. But learning line structures belongs to another class. So you don't have to worry about line structures here. Also, I'm not going to be, actually, I'm not going to go on the record. Okay, so let's see, what time is it? All right, we've got about 10. It's about 10 till 1. Let's look at a couple examples of just things that are a little trickier. I've told you that all along the way. These have all been exam caliber, but there's a couple that that are a little bit harder, and I like putting them on the test for that reason. I'm not promising these will be on yours, but these are often exam candidates. Let's draw the Lewis structure, in black preferably, for carbon monoxide, for CO. We're kind of regressing here, going back to a diatomic molecule here. You may look at this and go, this doesn't look so hard. Carbon has 4 electrons. Oxygen has 6. I know what to do. There's no charge on this sucker. I've got 10. 10 electrons. You don't even have to worry about a central atom because we just have carbon and oxygen, right? So let's spend 2 electrons to connect these two together. Now, let's complete some octets. Oxygen needs 6 more electrons to have a full octet. So let's spend those. Two electrons left. We're going to give these 2 to carbon. And now we're out. All right. We're out of electrons, but carbon still doesn't have a full octet. Now you may be going, Josh, this is not hard. This is nothing new. Let's take a lone pair away from oxygen, turn it into a multiple bond with carbon. And we're moving in the right direction. And we are, right? Carbon now has 6 electrons, but it still wants 8. You're like, I'm still not daunted. Let's do this again. You said this was a tricky problem for an exam, and it feels like one of the first ones we did. And if you're sitting there, eyes glazed, thoroughly unimpressed, I just want to say be careful, because it'd be very easy to get to this point in the problem, write it, and move on. And if you do, you'll be missing points. You'll be missing points because you haven't calculated your formal charges yet. Let's do that. All right. Oxygen, when it's neutral, has 6 electrons. In this structure, it has 3 bonds and 2 electrons in lone pairs. So oxygen has a formal charge of +1. Let's look at carbon. Carbon has 4 electrons when it's neutral. In this structure, it has 3 bonds and 2 electrons in lone pairs, giving carbon a formal charge of -1. This is the Lewis structure for carbon monoxide. Carbon monoxide is a neutral compound with formal charges. All right, that's what makes it tricky. So obviously, when you're dealing with an ion, you're like, okay, I'm in formal charge mode. I need to calculate formal charges. You also need to do that for neutral elements, because there are neutral elements out there with formal charges that are lurking. Now, some students feel uncomfortable with this because there's a negative on carbon, a positive on oxygen. And so some students will draw this structure and leave this as their answer. And they do it because when you calculate your formal charges, here oxygen we know has 6 when it's neutral. In this structure it has 2 electrons in bonds plus 4 in lone pairs, leaving us with none. And then you calculate carbon's formal charge. Carbon has 4 electrons when it's neutral. 2 electrons in, minus, it has 2 electrons in bonds plus 2 electrons in lone pairs. So it's also 0. So they think, isn't this better? But it's not. It's not, because carbon never breaks the octet rule. And in this structure, it only has 6 electrons. All right, so this is not the correct answer because it violates the octet rule. All right, so watch out for that guy. Okay, So I think we're going to wrap things up here. At this moment in time, you can tackle almost. Actually, I should leave with one comment. Note. So I'm not going to test you on these, but you should note that boron can break the octet rule by having 6 valence electrons. Only 6 valence electrons. So, for example, the Lewis structure for BH3 literally just looks like this. There's nothing you can do. All right. That's one thing you should be aware of. I'm not going to test you on it, but you should know it's out there. I think they might have you do one on a lab exercise worksheet. Second, if you draw the Lewis structure for NO, it'll come out like this. In this structure, nitrogen has 7 valence electrons. It's another exception that I won't test you on, but I know for a fact that it's on, I believe it's lab exercise 5. So it's out there. When you run into them, these are exceptions. They're not particularly stable compounds. Because they're reactive, they want to get 8 valence electrons, but know they're out there. It's okay to draw them. You didn't make a mistake if you get here. And I won't test you on these on exam 3. Cool? So with that, I'm going to officially bring lecture to a close. Do you guys have any questions, comments? Whoa. Comments, concerns. I know some people are already bouncing to other classes. But I'm totally down to hang if you guys have any anything that's on your mind at the moment. So at this moment in time, we made it through. We've covered all Lewis structures. On Monday, we'll be starting to talk about molecular geometry and Vesper theory. I've been in touch with your lab instructors. Hopefully, they're pushing back the due date for exercise 5, because exercise 5 not only does Lewis structures, but it also does molecular geometries, bond angles, all that stuff. So hopefully they're going to push that back because we're not going to talk about it till next week. So yeah, but at this moment in time, you can actually start working on exercise 5, because at this moment in time, you have all the knowledge that you need, to draw those Lewis structures. You can draw the Lewis structures, get to the best resonance structure, with the material we covered in today's lecture. Yeah. Yeah. Nobody had any questions. No one had any questions when I did my last OChem office hours on Monday. So I was, and like I tried to hang out for a little bit, just in case they just in case people are rolling in later or whatever. But you also can students can also submit questions through email. So when I've got no emails for an office hour, and then there are no Canvas questions, private messages sent in, and then the people who are hanging out live don't have any questions, I hang out for a little bit, but then if nobody shows up, nobody starts asking things, I just shut down the stream, because eventually, I don't know if, Raj, you've listened to it or not, but I basically spend that time free associating. And somehow I got from, I started talking about like French folklore. And I don't remember the exact stream of thought that brought me there. But it's just me talking into a microphone, and who knows where my mind will go, without some rails to run on, right? So it might happen again tonight. We'll see. I haven't received any, email inquiries so far, but they might come in at some point. So I don't know. We'll see how tonight goes. Tonight is for those of you who don't know, or maybe you're listening in, is tonight's my, OChem office hours for my OChem lab. Speaking of office hours, don't forget that, this Friday, every Friday, at 1:30, we have office hours. And by we, I mean Chem 400. So if you're struggling with material, if you are doing the homework and running into some trouble, totally hit me up. Now, Raj, how do I judge which atom is stronger? What do you mean by stronger? Do you mean more electronegative? Awesome. If you, let's see, like people say platinum is, that's okay. You're talking about like actual like physical strength. Honestly, so Vraj, that's a very interesting question. I don't know that there's necessarily a periodic trend for like, these metals are stronger. They don't break as easy as you go across the periodic table or up or down. But part of the problem is when people say platinum, or when people talk about any metal, it could be that they're talking about the pure metal. It could also be a compound, like the metal plus other elements to make different ores and stuff like that. So you don't really, when you talk about like strength, like tensile strength for, or like load bearing stuff for how easy it is for how brittle something is, how easy is it for something to crack. There's probably some general trends that run across the periodic table, but things vary drastically when you start doping in other elements and mixing ores and all that stuff. So I don't actually know off the top of my head, but I also can tell you that it's a more complicated picture because you can start, different elements will combine differently with others, and that combination can radically change the properties of a metal. So that's also at play in that situation. But that's an interesting question. Thanks for bringing that up. All right. So as a friendly reminder, we do have office hours every Friday at 1 p.m. If you're not able to log in and watch the stream live, you can still get your question asked. Email it to me, and I guarantee you I will get to it. I will answer it. You just got to do two things to make sure that I actually get your email. Make sure that the subject line is Chem 400 office hours, because about an hour or so before the stream, I go into my email and I search that. So it stacks up everybody who's submitting questions, so I make sure I get them all. And then also in that email with the question, attach a picture of the original problem. That way I can stack them all together and put them in a document so I can kind of scroll through them. It makes for a more streamlined feed or office hour session, as opposed to me flipping through pages in the book trying to find the specific problem. So if you could include a picture of the problem, I would definitely appreciate it. Okay, Diana, question. Is there a bonding trend on the periodic table? From the a bonding trend, from the perspective of is there a trend on like the types of bonding? Absolutely, whether we're talking about ionic or covalent, because those are based off of electronegativities, and electronegativities trend with the periodic table. In general, so yes, from that point of view, I don't know if that's specifically, if that's what you had in mind when you said bonding trend. But in general, when you pair more electronegative elements together, they'll make covalent bonds. When you pair electronegative elements with electropositive elements or low electronegative elements, then they make ionic bonds. So there's that kind of trend. Bonds between elements that are on the extremes tend to be ionic. Bonds between elements that are closer to each other tend to be covalent. Totally. Oh, so you're wondering about like strength of bonds. Yes. Is that what you're thinking? Like bond strengths based off the periodic table? So there is somewhat of a trend, and again, it's based off of electronegativity. So in general, the larger the difference in electronegativity, the larger that difference in electronegativity is between two elements, the stronger the bond they form will be. Ionic bonds are much stronger covalent bonds. So electronegativity is the trend. I should say is a trend. That has a great influence, or a strong influence, over bond strength. Totally. So it's like all connected, which is kind of cool. Totally. Okay, I think this is where I'm going to call this stream. It's been awesome hanging out with you guys. As always, I'm looking forward to diving in to molecular geometries with you on Monday and hitting whatever assorted random questions you guys may be struggling with in office hours on Friday. And again, if you can't tune in at 1:30, please send your question in over email. I will answer it to the best of my ability. And as always, I leave timestamps in the comments of each video, so you'll be able to find your specific question in the thread. You won't have to watch the entire video just to get the one answer you're looking for. Heck yeah. Alrighty, so yeah, it was great seeing everybody. I hope you take care. See some of you on Friday and everybody else on the flip side of the weekend. Later.